Okay, let's look at question 4, which is very interesting. We're told from the data in the table, determine the order of the reaction with respect to OCl, iodide, oxide, hydroxide, and the other order. So, equally here we've been given 3 reactants, and then we've been given the rate of formation. So we want us to determine the rate and also determine the value of the rate constant. That's part A. Part B, we are given the mechanism, consistency with a net equation, and of course with the lateral, which is rate determining step. Is it appropriate to refer to hydroxide as a catalyst in this reaction? So let's first of all answer them in the order we are given. So first of all, let's find the lateral. So in this case, these are assumed to be the reactants that we've been given, right? So we are supposed to find the lateral in respect to these 3. So if we're going to come up with an equation, we can say let R be equal to K, and then we have 3 distinct reactants, okay, as you can see. So now all these are going to be raised to different powers. Let's call them A, B, and C. Okay, so what is our goal? Our goal is to find the powers of the values of A, B, and C. Those are going to be the orders in respect to the reactants, and of course will give us a lateral. Okay, so equally, if you're able to remember in the other question, we are looking for cases where the other 2 are going to be constant, right? So which cases? Let's call this one experiment 1, 2, 3, 4, and 5. So if we're going to look at experiment 1 and 3, so the first reactant is different, the other 2 are the same. So I gave you a tip on how to go about it. How do you go about it? So how you go about that is ignore the ones that are the same and just substitute in the cases where they're different. So which one has got bigger values if you compare 1 and 3? So I can see that 1 has got a bigger value, so I'll go for 1 to be the first one. So substituting in that equation that we have of our lateral, the rate is 4.8 for experiment 1 times 10 to the power negative 4, and then equal to K. Then the reactant that is changed was this one. So that was 0.0040 to the power what? That is to the power A. Everything else was the same. So we know if we're going to divide by the other experiment, they are automatically going to divide. So we'll divide by the third experiment now. The rate there was 2.4 times 10 to the power negative 4 equal to K. And then of course for the first reactant it was 0.0020, also raised to the power A. So we're just getting the data of experiment 1 and 3 and then substituting in the equation of our lateral. Okay, if we're going to put the other parts for the other 2 remaining reactants, they are all going to be of the same data and they're going to divide. Okay, as you can see they are the same, so no need of us showing them there. If you want you can show them, no problem. So if we're going to divide 4.8 by 2.4, it's going to be a 2. The k's will subtract. Since we've got the same power there, if we divide what's in the brackets, we're going to get a 2. We'll maintain the power. So therefore, A automatically becomes a 1. So we found A. A is equal to 1. So we can now take another step and try to find the values of other letters as well. So experiment 1 and 3 has already worked. Let's try to identify some other experiments that may help us. So if we look at 2 and 3, first one is the same, third one changes. So we're going to now find iodide. So how do we go about it? So equally we substitute in the same equation. Which one's got bigger values? 2 has got bigger values. So 5.0 as the rate times 10 to the power negative 4, and then a constant K. So this one is the same and hydroxide is the same, so we'll leave them out. Focus on the iodide, which was 0.0040 raised to the power what? B, divided by the second it's the third experiment. The value becomes 2.4 times 10 to the power negative 4 equal to K. For the iodide there it was 0.0020. The power B as well. So what we have, so 5.0 divided by 2.4. So we're going to have 2.0833 equal to K will cancel out, and then 0.0040 divided by that is going to give us a 2. Since the power is the same, we'll maintain it. So we're not interested in those values. Okay? So therefore B becomes 1. So B is equal to 1. Try to identify the others as well, where the other two are going to be constant, and then find the power of the hydroxide. So which experiment do we have this reactant and that reactant the same, and then the other guy is different? Try to pay attention, try to observe. So it's actually 3 and 4. These two are the same. That is unique. Okay, so starting with the fourth experiment, we have 4.6 times 10 to the power negative 4 equal to, so I'll ignore the first one and the second one, and then I'll go to hydroxide. Hydroxide at 1.00 to the power C over 2.4 times 10 to the power negative 4 is equal to K, and then of course we're dividing by, is it 0.50 the power C. So grab whatever you have, grab what you have, and then try to divide. So let's be careful on what we've done here. What have we done? So the first experiment that we've put on top is fourth experiment. So 4.6, 0.5. So I've actually swapped there. There it was supposed to be 0.50, and then at the bottom you have 1.00. So 4.6 divided by 2.4 is going to give us 1.917 is equal to, K will cancel out, 0.5 divided by 1 it's going to be what? 0.5 over 1. 0.5 there it's a 1, there it's going to be a 2. So we have 1 over 2. Just the power C. Now I said 1 over 2 is the same as 2 to the power negative 1. So 1.9, we want to deal with our numbers here. So let's take that as a 2, considering experimental errors. And then that will be 2 to the power negative C. So negative C can be equated to 1. And then C becomes negative 1. So C therefore is equal to negative 1. So therefore, the lateral becomes R is equal to K, first reactant OCl negative, raised to the power 1, iodide to the power 1, and then hydroxide to the power negative 1 can be on the bottom with a positive power. So this is our lateral. What is the overall order of the reaction? Was also a question that we needed to answer. Determine the order of the reaction with respect to the reactants, and then the overall order. The overall order requires you to add 1 plus 1 plus a negative 1, which gives us a 1. That's the overall order of the reaction. What else? We're supposed to find the value of the rate constant. So to find the value of the rate constant, get any experiment of your choice, substitute in the given data that we have. Okay? And then try to find the value. So I can go for experiment 1. Okay? And then I'll plug in the values that we have. So for the rate for the first experiment, we had 4.8 times 10 to the power negative 4 being equal to K. and then you can plug in for the other reactants. So for HCl, it was 0.0040, and then for the iodide it was 0.0020 divided by the hydroxide, which was 1.00. Okay, so our goal there is to find the value of K. So let's try to punch all those on the calculator there. 0.0440 times 0.020 divided by 1. Okay, and then we should be able to find the value of K. So the value of K I'm getting is 60. Now the fact that this is the first order reaction, the units are second negative. If you are going to plug into our formula for finding the units, it's m1 minus n and then second negative. So n is 1 as over order, so we just remain with second negative for this part of the question. Now B becomes very interesting in that we are taught to show that the reaction mechanism given below is consistent with the net equation. So let's try to test and see if it's going to be stoichiometrically correct, and let's try to show. So all we do is to add all these steps we have. That's all we do. Cancel what's appearing on the opposite sides. Okay, so let's start. I can see this guy is appearing on opposite sides. I can see hydroxide is appearing on opposite sides. I can see water is appearing on opposite sides. I can see, what else can I see? This guy is also appearing on opposite sides. So what remains on the reactants are only two. So OCl negative plus iodide negative. And then on the right we have Cl negative plus OI. So if you try to observe this one, it's stoichiometrically correct, right? So Cl, so that's correct. Okay, and we can clearly see that all these two reactants we have are basically part of the lateral that we determined. What was our lateral previously, if you saw from the previous question? So our lateral was K OCl negative, iodide, and then of course hydroxide. So we can see that both reactants that have come up are part of the lateral, so which is proves this to be correct actually. Okay, so it's not always going to be necessary that all the reactants are supposed to be in the lateral now. So now there's another segment of the question that we need to focus on, which is determining which one is the rate determining step. And of course, because of the fact that we have to show, so let's be careful. So if we try to observe again our lateral, we can see that we have OCl negative, iodide negative, hydroxide negative. So let's first of all try to determine the laterals in respect to this, because the rate determining step is a slow step. Okay, if you are new to reaction mechanisms, I would recommend you watch a video about that on our site. It's about 1 hour, so you understand the idea of reaction mechanisms. Reaction mechanisms should be able to give you the net equation, should be able to give you the lateral as well. So let's see which guy can give us a lateral. Okay, so we have to come up with a laterals for both the backward and backward reaction for the reactions that have a species appearing in the lateral. So if you look at the first one, for step 1, if we look at the reactants, we can see that the first one is appearing in the what? In the lateral. So we're supposed to write the lateral for that one. So lateral for the forward reaction becomes, so we'll write them based on the stoichiometric coefficient. So OCl negative and then water. Are we interested in the backward reaction? If we try to observe, we can see there is hydroxide, which is also part of the lateral, so we can also write it. So for B, for the backward, so that would be HOCl and then hydroxide. And then for, so apparently we're assuming that one to be an equilibrium reaction. Okay. So, and then for step 2, for a forward reaction, we can see that iodide is part of the electron. For a backward reaction, we don't have anything, so we'll only focus on the forward. So our rate for step 2 becomes K iodide and then HOCl. By the way, if you had a 2, for example, on water, it would mean the power would be 2. So we are raising this based on the stoichiometric coefficients. And then for step 3, for the reactants, hydroxide is there. So we have to show it. Backward reaction, none of the 2 are part of the electron, so we can just ignore them. Now, which one is the rate determining step? Is it step 1, 2, and 3? So we can disqualify a few here. The ones having hydroxide in the electron is appearing on the denominator. Now, if you check where it's appearing, it's on top. It's a numerator, so those ones are automatically disqualified. Okay, so disqualified, they can't be the rate determining steps because they're contradicting the electron itself. So we've removed the backward for the first step 1 and also step 3. Now if you check the first one we have OCl minus and water. So this is matching up, but water is not. If you check step 2, iodide is matching up, but HOCl is not. So we have to choose between the two, which one is most likely to be the rate determining step. Now for water, if you check water is there, and then it's also there. But if you check the other reactant, HOCl, we'll notice that it's an intermediate. Just upon it being produced in the first experiment on the first reaction, it's taking part in the reaction in the second one. So that one, at least we can make some changes to it. So most likely step 2 is the rate determining step because it's containing an intermediate, and then one of which reactants is also matching up with the electron there. So don't forget, this is K and then OCl minus. So for the intermediate, we can actually substitute it. We can substitute it with something. That's a good part about intermediate. So where is an intermediate appearing? In the step 1 and also step 3. So let me do something here. So we can actually combine step 1 and step 2. We can first of all focus on step 1. So if we look at step 1, we can combine the backward and the forward by equating them together. So if we equate them, K for the forward, that's for the forward. The backward is K HOCl hydroxide. Our goal is to make the intermediate the subject. What do we end up with? So this is forward, that is backward. So divide by K backward and then hydroxide. So on the left, on the right, those ones will divide. So HOCl becomes a subject in that one. Okay. So step 1 has given us an expression for what? It has given us an expression for the HOCl by making it the subject, right? Now, in the assumed rate determining step, we said it's step what? Step 2. Now step 2, the electron for step 2 was what? Ri is equal to K iodide and then the intermediate HOCl. So we've come up with an expression for HOCl from step 1, so we can substitute in that equation. So if we're going to substitute, we're going to have K iodide Now on HCOCO we're going to put this O part. Okay, so let me just move it. There we have it. So all the k's can be multiplied together, they can divide together to form 1k. So this k multiplied by that k divided by this k is just a constant. And then remain with iodide on top. Okay. And then OCl negative over hydroxide on the denominator. Now water, since the concentration of water does not change, can be taken to be a constant and so omitted in the lateral expression. So you notice that actually step 2 is a determining step in that it has given us a lateral which is matching up with a lateral which we determined experimentally. Okay? So step 2 is the determining step. It's a Stroll reaction there. Now C says, is it appropriate to refer to hydroxide as a catalyst in this reaction? Now if you check hydroxide, it's actually part of the denominator. If you're going to increase this concentration, the reaction is going to be, the rate of the reaction is going to be slowed down because the rate and hydroxide are inversely proportional. If you increase hydroxide, it means the value there will reduce. It's like if you've got R being equal to 1 over X. If X becomes 100, it means that value will reduce. If it becomes less, R will increase. So it is not a catalyst because it doesn't speed up the rate of the reaction. Instead, it slows it down. So we can instead call it an inhibitor instead of it being called a catalyst.